All right, guys. So in this video, what we're going to be doing is we're going to be going over the log floating in water problem. So let me get this out. So what our problem looks like, we have a log floating in water. And the top of the log is h above the water level. Now we're assuming the log is a perfect cylinder with a length of L. Excuse me. So since this is not sinking, not moving, we can go ahead and assume velocity is equal to 0. And since velocity will not change, acceleration is 0, this log is going nowhere, the net force on that log must be 0. So if we draw a free body diagram, we're going to have two forces on it. The weight of the log, and then the buoyant force, or the force of the water pushing back up on the log. So, to satisfy our equation, F net, which is equal to 0, must be equal to the buoyant force subtracted by the weight of the log. So what's going to happen is we're going to move weight on the other side. We're left with weight of the log is going to be equal to the buoyant force. Excuse me. So the cool thing about buoyant force is it's equal to the weight of the liquid displaced. So just like we did with the log, weight is just mass times gravity. So mass of the water displaced times gravity. So we're going to have mass of the log equal to the mass of the water displaced, both multiplied by gravity. So since they're both multiplied by gravity, we can get rid of those. And we're left with mass of the log must be equal to the mass of the water displaced. All right, there you go. So what's going to happen here is another way to say mass is just density multiplied by volume. So the mass of the log is density of the log times the cross-sectional area. So the radius of this multiplied by the length, so that's a cylinder, would be pi r squared times L times the mass of the water, equal to the mass of the water, so the density of water multiplied by the cross-sectional area, so in this case the area under the water, I'll call it AW for right now, area of the water underneath, multiplied by the length. Notice length, same thing as gravity, we can get rid of those. So we're left with the density of the log times the area of the circle must be equal to the density of the water times the area underneath the water. So let's solve for the density of the log, and we're left with the density of water times the area under the water over the area of the circle. So what we need to find now is the area underneath the water. So if we took a side view image of the log, we'll notice all this area down here is the area of the water, or area underneath water. And so to get that, AW must be equal to the total area of the circle minus the area of this top part, which I'll call H. So how we find AH? It's over here. So AH, now draw an equal sign real quick. Will be this area right here, where the length of this semicircular shape is H. I'm going to draw in these lines here. So what these lines are the radius. So if we draw the center here, and we draw the lines here, this is what the lines are. It's the R connecting the 2 points where the log meets the water. So, since this entire area will be R, the length from here to here will have to be R minus H. Then you're going to have 2 thetas here, which means total theta of the whole region area is going to be 2 theta. So to get the area of the entire of this sectional area, it is just theta total over total number of radians in a circle, 2 pi, multiplied by the total area. So if we plug in our theta total, notice the 2's will cancel out, so we're left with theta over pi times pi r squared. Notice pi's will cancel out, and we're left with theta r squared. Now we have to find out how to get theta. Notice these two triangles are right triangles. So we can use cosine relations to equate r over the ratio of r minus h over r. So it means cosine of theta is r minus h over the hypotenuse, which is r. Get theta, just the arc cosine of r minus h over r. So now our area of the section is arc cosine of r minus h over r times r squared. So remember, to get the area of the water, or the area underneath the water, it will be the total area of the section minus the area of the log outside the water, or AH. So we got this now. Now we need to find AH. Or no, I mean, my bad. Total area minus AH. To get AH, we're going to take the sectional area and subtract the area underneath, so the triangle. So we go back to our shape. This right here is an unknown length, which we'll just call B, because it'll be the base of the triangle. And recall that a triangle's area is 1/2 base times height. So to get the area of this, it'll be 1/2 base times r minus h. Now we need to find the base. So notice, since these are right triangles, we can apply Pythagorean theorems to it. And since this is equal both sides, you can say this side will be 1/2 b. So we have 1/2 b squared plus r minus h squared equal to r squared. Let's get this on this side, and we're left with 1/2 b squared equal to r squared minus r minus h squared. Then what's going to happen here is we're going to square root both sides, so we're left with 1/2 b is equal to the square root of r squared minus r minus h squared. Take the 2 over, and we have our value for the base of the triangle. It's just 2 times the square root of r squared minus r minus h squared. And so if we FOIL this, what we're going to end up with is r squared minus 2rh plus h squared. So notice we have this minus sign here. So it'll be minus r squared plus 2h minus h squared. So notice we have an r squared here, so these will cancel out. And we're going to be left with 2rh minus h squared. So now that we have our base, we can plug that in to our area of the triangle formula we found up here. So area of the triangle equal to 2 square root 2rh minus h squared times r minus h times 1/2. Notice the 1/2 and the 2 will cancel out, leaving us with r minus h times square root of 2rh minus h squared. Not what I meant to, gosh dang it, not what I meant to do. So now that we have our area of the triangle, we can now find AH. So it'll be the area of the section. So r squared, r cosine of r minus h over r minus the area above the water. I mean, the area below the water, the triangle, which we found right here. So r minus h of 2rh minus h squared. So now we can finally calculate the cross-sectional area of the water displaced, which is just the total area, pi r squared, minus the AH, which is r squared, r cosine of r minus h over r. Keep in mind, this is a minus, so now this will become a plus. R minus h, square root of 2rh minus h squared. So with the cross-sectional area for the water, we can go back to our very first equation. We're solving for density of the log, where now we have density of the water times the cross-sectional area of the water over the area of the log. We now have the area of the log, area of the water, And we can look up density of water, which is just 1,000 kilograms per meter cubed. Let me try that again. Please don't crash, please. All right, let's try this again. All right, so as I was saying, our cross-sectional area of the water we can now plug in, and our area of the log we know as pi r squared. So density of the log will have to be equal to 1,000 kilograms per meter cubed of pi r squared minus r squared times the arc cosine of r minus h over r, or the height from the radius, from the center of the circle to the top of the water on the log, plus that same value, r minus h, multiplied by 2rh minus h squared, which will be the length of the water from one side of the log to the other. Or in other words, this point from here to here. Or, well, half of it, I mean. All of this over the area of the log, which is pi r squared. And so with that, we have an equation for the density of a floating log given the radius and the height. Now, of course, this equation assumes that the log is a perfect cylinder. That's besides the point, but here's the equation. I'll post a link to the notebook in the video description if you want to look at it. But otherwise, thanks for watching.